Next topic is linear span. Let V be a vector space and S is the set V1, V2, Vn is the set of vectors in V. That is, these V1, V2, Vn are the elements of this vector space V. Then the linear span of S is denoted by Ls. It's called linear span of S and is denoted by notation capital S, capital L in bracket S is defined as this ELS is defined as K1 V1 plus is the set of K1 V1 plus K2 V2 plus Kn Vn such that K1 K2 Kn are scalars or belongs to R. Okay, so this LS is what is the set of all types of linear combination of V1 V2 Vn, all types of uh, just change K1 K2 Kn, take K1 K2 Kn as a scalar, different scalars. We have the linear combination V1 V2 Vn, linear combination. This K1 V1 plus K2 V2 plus Kn Vn is what is the linear combination of V1 V2 Vn. So what is LS? LS is the set of all linear combinations of V1 V2 Vn, all possible linear combinations of V1 V2 Vn. So this is the linear span and is denoted by LS. So the set of all linear combinations of V1 V2 Vn. For example, suppose S3 is 1 and minus 1. Then what is S3? LS3 is K1 into 1 plus K2 into minus 1 such that K1 and K2 belongs to R. And so what are the linear combinations? Just change K1 and K2. Suppose K1 is 1 and K2 is 2. Then we have the element 1. Suppose K1 is 2, K2 is also 2. We have this 0 as the element. Suppose K1 is minus 1, K2 is 2. We have the another element. In this way, we have, suppose K1 and K2 are, we take fractional. Suppose K1 is 1 half, K2 is 0. Then we get the 1 half element. And in this way, we have all this is the set of all real numbers. We have all real numbers. All real numbers are linear combination of this 1 and minus 1. And therefore, it is equal to R. This LS3 is what? Is equal to R. And that is this set 1 minus 1 spans R3. So what is, if you take S3 as singleton 1, then also we get LS3 is a set of real numbers R. Because what are the scalar multiples of, then what is LS3? If S3 is singleton 1, then LS3 is K1 into 1, such that K1 belongs to R. That is all the linear, all the multiples of 1. So what are the multiples of 1? We have all the elements. Suppose if you take a K1 is 0, then we have 0 element. If K1 is 1 half, then we have 1 half element. In this way, we have all the elements. So if we take S3 as singleton 1, then also LS3 is a set R, set of real numbers. We have all real numbers. So the note is this: LS is V. If LS is V, so this LS is itself a vector space V, then we say that S spans V or S span V, or we say V span by S. So in all cases, LS is not equal to V. So in some cases, if LS is equal to V, then in that cases, we say S spans V or V span by S. So S3 in this example, LS3 is R, and so we say S3 spans R as LS3 is equal to R. Okay, so in this way, LS is equal to V, that is S spans V if and only if every vector of V is expressible as a linear combination of vectors in S. Because when LS is equal to V, LS, these two sets are, when these two sets are same, if they are subsets of each other, that is ELS is subset of V and V is subset of ELS. So obviously or clearly ELS is subset of V, because what is ELS? The ELS is the this set. This is the set of all linear combination of V1, V2, Vn. Suppose ES is the set contains element V1, V2, Vn. Then what is LS? LS is the set of all linear combinations. And obviously this K1 V1 plus K2 V2 plus Kn Vn belongs to V for all K1 K2 Kn, because V is a vector space and therefore V is closed for addition, V is closed for scalar multiplication. So V1 is the element of V, so K V1 is the element of V. V2 is the element of V. So for any scalar K2, K2 into V2 belongs to V. In this way, Kn into Vn belongs to V because Vn is the element of V, and therefore for any scalar Kn, Kn into Vn belongs to V. And this K1 V1 plus K1 V1, K2 V2, Kn Vn, all are the element of vector space V, and therefore their addition also element of vector space V, because V is a vector space, means V satisfies all the 10 properties. That is, V is closed for addition, V is closed for scalar multiplication, and therefore this addition of all these scalars, scalar multiplication belongs to V. And therefore K1 V1 plus K2 V2 plus Kn Vn, this element belongs to V for all K1 K2 Kn, uh, for all K1 K2 Kn belongs to R. That is, LS is obviously subset of V. So when LS is equal to V, when we know that when A is capital A is equal to capital B, if A is subset of B and B is subset of A. So when LS is equal to V, these are the two sets. LS is the set, V is the set, and when these two sets are equal, if they are subsets of each other. So obviously LS is subset of V. No need to show LS as a subset of V. In case of, if we have to show LS is equal to V, then we have to show LS is subset of V. But obviously, clearly, LS is subset of V, and so now we have to show just V is subset of LS. So when V is subset of LS, if each element of V belongs to LS, and when element of V belongs to LS, so the LS is the set of all these type element. This is the LS contains the elements of the scalar the this is the linear combination of V1 V2 Vn. Every element of LS is the linear combination of V1 V2 Vn. That is, if you take any element from V, capital V, vector space V, and if it is expressed as a linear combination of V1 V2 Vn, then it belongs to LS. That element belongs to LS, and therefore when V is subset of LS, if every element of V is a element of LS, that is, every element of V is expressed as a linear combination of elements in S, then in that case V is subset of LS. So if you have to show S spans V or LS is equal to V, we have to show that every vector of V is expressible as a linear combination of vectors in S. So remember these things. That is, if I have to show LS is equal to V, or if I have to show S spans V, or S span V, or V span by S, what do we have to show? We have to show every vector or every element of this capital V is expressible as a linear combination of vectors in S. So now the examples. So this is the definition of linear span and the vector span, space span by S. So show that this set S contains three elements 1 1 1, 0 1 1, and 0 1 minus 1 spans R3 or span R3. This is R3 is a vector space. And in the second case, we have to show this set does not span R3. Okay, this set does not span R3. So now the answer of the first example, what we have to show? To show S span R3. Yes, this set spans R3. That is, LS is equal to R3. When we say S span R3, if LS is equal to R3. And when LS is equal to R3, this note that when LS is equal to V, if every vector of V is expressible as a, so when LS is equal to R3, if every vector of R3 is expressible as a linear combination of vectors in S, then in this case we say LS is equal to R3, or we say S spans R3. So when LS is equal to R3 or S spans R3, if every vector of R3 is expressible as a linear combination of vectors in S. Now what we have to show? We have to, so this R3 contains infinitely many vectors, and we have to show every vector or each vector of R3 is expressible as a linear combination of these three vectors. So for that we take any vector from R3. Let U bar is equal to ABC, belongs to R3 be any element, be any vector from R3. And now we have to show this ABC is expressed as a linear combination of these three elements. So already the previous chapter, the previous topic is what? The linear combination. So we know the procedure of this element to express the linear combination of these three elements. So if I have to express this element as a linear combination of these three elements, then what is the procedure? The first sentence is let K1, K2, K3 be scalar such that U bar is equal to K1 V1 plus K2 V2 plus K3 V3. Substitute U bar, V1 bar, V2 bar, V3 bar and find the values of K1, K2, K3. And if this K1, K2, K3 does not exist, then in that case we say the vector is not linear combination. Vector is not linear combination of the three vectors or two vectors. So here we have to express this ABC, this U bar as ABC as the element of R3 as a linear combination of these three elements. Okay, and in the second case, we have to show this ABC is not linear combination of these three elements, because we have to show in the second example this set does not span R3. So when the set does not span R3, if LS is not equal to R3, or if every vector of R3 is not expressible as a linear combination of vectors in S. So here in this example number 1, we have to show this vector U bar as ABC belongs to R3 as a vector of R3 is expressed as a linear combination of these three vectors of S. So what is the procedure? Let K1, K2. So this is the topic, repetition of topic, linear combination. We have to express a vector as a linear combination of the given three vectors or two vectors. Here we have to express this U bar as a linear combination of V1, V2, Vm. So what is the first sentence? Let K1, K2, K3 be scalar such that U bar is equal to K1, V1 plus K2, V2 plus K3, V3. And then substitute U bar, V1 bar, V2 bar and V3 bar. And now apply the definition of scalar multiplication. We have this. Then apply the definition of addition of vectors in R3. We have this. So R3 is a vector space, and R3 is a vector space means there are two operations: addition of two vectors and scalar multiplication. And what are the operations on R3? As a usual scalar multiplication and usual addition. So by using that two definitions, we have this, and then compare the LHS and RHS. We have K1 is equal to A, K1 plus K2 plus K3 is equal to B, and K1 plus K2 minus K3 is equal to C. Now we have to solve these equations. So we solve these equations by this method, by adding and subtracting these two equations. Okay, that is substitute K1 in the second equation and then solve the equation for K2 and K3. This is the procedure. But instead of this, or instead of any method, what we have to do? We use the Gauss elimination method. Don't use these methods. These methods are, this method is complicated. In some example, this becomes complicated. So for any system, if you have to solve the system, use the Gauss elimination method. So what is the Gauss elimination method? Form the augmented matrix. So don't write this calculation. Okay, this is your trial and error method, that K1 is substitute K1 in the second and all these things. So instead of this, apply the Gauss elimination method. So we have to solve these three equations and we have to find the values of K1, K2, K3. So either this system is consistent or inconsistent. So when the system is inconsistent, if the rank of A is not equal to rank of AB, and when this system is consistent, if rank A is equal to rank AB. Okay, so we'll form the augmented matrix. So it is 1, 0, 0, A, 1, 1, 1, B, and 1, 1, and minus 1, C. Now this matrix is the matrix A, and this ABC as a column matrix ABC is the matrix B, and this is the combination of A and matrix B. So this is AB matrix, A oblique B matrix. Okay, so we have to reduce this matrix to echelon form. So this is the element 1. So we have to reduce these two elements as 0. So operation are R2 minus R1 and R3 minus R1. So we have 1, 0, 0, A, 0, 1 minus 0, 1 minus 0, B minus A. And then 1 minus 1, 0, 1 minus 0 is 1, minus 1 minus 0 is minus 1, and C minus A as the element, C minus A. Then we have to reduce this element as 1, but it is 1. So we have to reduce this element to 0. So R3 minus R2 as the application. So first row and second row as it is. So 0, 1 minus 1 is 0, and minus 2 here. And then C minus A minus B minus plus A, we have this B minus C. Okay, minus B, C minus A minus B plus A. So minus A plus A get cancelled. So we have C R3, C minus B, C minus B as the element right here, C minus B. It is not R3 minus R2. So R3 is what? C minus A minus B plus A. So C minus B, right? The C minus B as the element. It is not minus C plus B. It is C minus B. So R3 minus R2. C minus A minus B plus A. Minus A plus A get cancelled. So C minus, right here, C minus B. And then we have to reduce this minus 2 as the element 1. So multiply by minus 1 half to R3. So we have the element 0, 1, 0, 0, 1. And here we have minus 1 half into C minus B becomes minus C plus B divided by 2. After negative effect of negative, this minus 1 half. So we have minus C plus B. If you absorb this minus sign, then if you multiply by minus C minus B to by minus 1 half, then we have minus C plus B divided by 2, or B minus C by 2. Okay, and this is an echelon form of this matrix AB. And what is this? The rank of the now AB, this whole matrix is the echelon form of the matrix AB. So what are the, how many non-zero rows in this matrix? 1, 2, and 3. All these 3 are the non-zero rows, and therefore rank of AB is 3. While this matrix, after cancelling this last column, remaining matrix is what? Is the echelon form of the matrix A. And this matrix also contains 3 non-zero rows. This is non-zero row, this is non-zero row, and this is also non-zero row. And so rank of A is also 3. And so rank of A is equal to rank of AB, and therefore the system, given system, is consistent. So if the system is inconsistent, then we say K1, K2, K3 does not exist, and in that case we say this ABC is not linear combination of these 3 vectors. But here the system is consistent. Now we have to find the values of K1, K2, K3. So rewrite the equation. So we have K1 into 1 is K1 plus 0 into K2 is 0. 0 into K3 is equal to A. Then next equation K2 plus K3 is equal to B minus A. And last equation K3 is equal to minus C minus B divided by 2, minus in bracket C minus B by 2. And therefore K2 is, after K2 is what? B minus A minus K3. Minus K3 means this. So plus B minus C by 2. After simplification we have 3B minus 2A minus C by 2. And so K2 is this. We have K2 as 3B minus 2A minus C divided by 2. And we have K1 is A, K2 is B minus 2A plus C by 2. Whatever may be it, B minus 2A plus C by 2. So substitute this K3 in the above equation, we have K2. So K2 is B minus 2A plus C by 2. And K3 is what? In bracket, minus in bracket C minus B by 2. So we have the values of K1, K2, K3, and therefore we say that ABC, round in round bracket, U bar is equal to ABC is expressed as a linear combination of the 3 vectors of this set S, V1, V2, V3. So U bar expressed as a linear combination of V1, V2, V3, and therefore we say that the set S spans R3, as this set spans R3. So when we say the set does not span R3, if this vector ABC is not expressed as a linear combination of V1, V2, V3, and we know that when ABC does not express as a linear combination of V1, V2, V3, if this K1, K2, K3 does not exist, means this system, if this system is inconsistent. And when this system is inconsistent, if the rank of A is not equal to rank of AB, or we have the some absurd sentence. If you observe the previous example, does not this example, okay, in this case what happened, in the second example of linear combination, this set is not linear, this vector is not linear combination of these three vectors. How can show this? If we solve the system, then what do we have? We have the 0 is equal to 1 as the absurd sentence, impossible sentence, wrong statement. And that is, we say the system is inconsistent. Or in another way, we say that rank of A is 2, rank of AB is 3, and these two are not equal. And therefore, the system is consistent. And this means K1, K2, K3 does not exist. And so U bar as a is not linear combination of V1, V2, V3. So the second example, this is the use to second example. So what is the second example? We have to show now this set, this is the another set, yes, that 2, -2, 3, 4, 1, 2, and 8, 1, 8 does not span R3. So we have to show LS is not equal to R3. That is, every vector of R3 is not expressible as a linear combination of vectors in S in the second case. If the question is like that, determine whether this set spans R3. Then we start with that in assumption that we have to express, we have to show LS is equal to R3. So we have to show LS is equal to R3. In this case, we have to show the set does not span R3, means we have to show LS is not equal to R3. That is, every vector of R3 is not expressible as a linear combination of vectors in S. So take U bar as ABC belongs to R3, be any element, be any vector. Now we have to show this vector is not expressible as a linear combination of vectors in S. So we will start with the first sentence that K1, K2, K3 be scalar such that U bar is equal to K1 V1 plus K2 V2 plus K3 V3. Now we have to find the values of K1, K2, K3. So substitute U bar, V1 bar, V2 bar, V3 bar. So the answer of the problem of spanning and does not spanning, both are same. So substitute U bar, V1 bar, V2 bar, V3 bar, and then apply the definition. Apply the definition of scalar multiplication and then vector addition. We have the three equations after comparing LHS and RHS, and therefore we form the augmented matrix. From this, we form the augmented matrix. It is 2, 4, 8, and then A -1, 1, -1 B, 3, 2, 8 C, and then we have to reduce this matrix to echelon form. So reduce this 2 element to 1. So the application is R12, interchange the first and second row and change the sign of first row. Then so we have 1, -1, +1, -b as the first row. So after two operations, interchanging the rows first and second and change the sign of first row, we have this matrix. Then we have to reduce these two element as 0. We have to reduce the first, in the first step at this place 1. Then we have to reduce these 2 and 3 to 0. So the operation are R2 - 2 R1 and R3 - 3 R1. So first row as it is, the second row is 0, and then we have the this minus +2 +4 is then 6, then plus -2 +8 6, and in this way A minus +2b. Then we have 0, 5, 5, and C +3b after this application R3 - 3 R1. Then we have to reduce this 6 as 1. So the operation is R2 - R3. So after, because of this, we can, instead of this, we can also apply the application transformation 1/6 R2. But by applying 1/6 R2, we have 1 at this place, 1 at this place, but we have the fractional number at this place, and it's somehow difficult to calculate the further calculations. So in order to avoid the fractional numbers, we apply this application. Or this is not wrong application, that 1/6 R2. We can also apply the 1/6 R2. That's depend on your choice. So here the application R2 minus R1 in order to reduce this 6 to 1. So we have this. After applying this 6 minus 5 is 1. And then A plus 2B minus C minus 3B becomes C plus 3B. Okay. So A plus 2B minus C minus 3B. I think here something is wrong. Okay, yes, it is not wrong. It is C plus 3B. That is the last row as it is. The change in second row. So A plus 2B minus C minus 3B becomes A minus C minus B. Yes, it is correct now. And then we have to reduce this 5 to 0. So the application is R3 minus 5R2. So we have 0, 0. And here we have 6C minus 5A plus 8B after R3 minus 5R2. Okay. And this is an echelon form. This is an echelon form. This is an echelon form. And so what is the rank of A? This first three columns are the echelon form of the matrix A. And the rank of A is 2. And if this whole matrix is the echelon form of the matrix AB, and if you consider the first row, it is non-zero, second row non-zero, and third row also non-zero. When it is non-zero, the third row, if this quantity is not equal to 0, 6C minus 5A plus 8B is not equal to 0. And we know that this 6C minus 5A plus 8B is not 0 for all ABC. It is 0 for some ABC. So it is not always 0. And therefore, the rank of AB is 3. And therefore, rank of A is 2 and rank of AB is 3. These two are not equal, and therefore the given system is inconsistent. And therefore we say that, so write these 10 statements, and then we say that this ABC is not expressed as a linear combination of V1, V2, Vn, and therefore we say LS is not equal to R3, or we say yes does not span R3. The set does not span R3. So write that sentence. Or after rewriting like this, after augmented matrix, after rewriting, if you observe the previous example, so after rewriting the equations, what we have? We have the first equation as K1 minus K2 plus K3 is equal to minus B, K2 plus K3 is equal to A minus C minus B, and last equation is 0 is equal to 6C minus 5A plus 8B. And this is not true for all ABC. So the last statement equation is absurd for some ABC, and therefore every vector of R3 is not expressible as a linear combination of V1, V2, V3, and therefore we say that the set does not span R3, or the three vectors do not span R3. Okay, so the second example is the example of do not span. So similarly, this 1 0 0 0 1 0 and 0 0 1 spans R3, because if you take any vector ABC from R3, then it expressed as A1 0 0 plus B0 1 0 plus C0 0 1. So just A, B, C are the K1, K2, K3, and therefore every vector of R3 is expressible as a linear combination of these three vectors 1 0 0 0 1 0 0 0 1, and therefore this set span R3. Okay, similarly 1 0 0 1 spans R2. Similarly 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 1 span R4. In this way, the set of n tuples 1 0 0 0 0 dash dash 0 0, that is the 0 1 0 0 0 dash dash 0 0, and then in this way the last element is 0 0 0 dash 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 1, that is the set of n tuples spans R raised to n. Okay, and therefore in this way 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1 spans M2 by 2R. This set spans M2 by 2R. How we can show this set spans M2 by 2R? If you take we have to show every vector of M2 by 2R expressed as a linear combination of these four vectors. So take any vector as a 2 by 2 matrix A, B, C, D from M2 by 2R, and then we can express that vector A, B, C, D as a linear combination of these four vectors as A into 1 0 0 0, plus b into 0 1 0 0 plus c into 0 0 1 0 plus d into 0 0 1 0. And therefore every vector of m2 by 2 are expressed as a linear combination of these four vectors, and therefore these four vectors of this set spans m2 by 2r. Similarly, 1x x square spans p2x or p2. What is p2x? P2x is the vector space of all polynomials of degree less than or equal to 2. And these three vectors, 1, x and x square, actually these are the three polynomials, 1, x and x square, spans p2x. Because if you take any vector, any element from p2x, for example, a2 plus, suppose a0 plus a1x plus a2 x square as the element of p2 is any element, and actually this vector is a linear combination of these three vectors, 1 x and x square, and therefore every vector of p2x expressed as a linear combination of 1 x and x square, and therefore this set spans p2x. In this way, n1 x x square dash 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 x raised to n spans p and x. That is this set contains three elements, and that set 1 x x square dash 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 x raised to n contains n plus 1 vectors elements. That set spans p and x or pn, set of all polynomials of degree less than or equal to 1. So these are some examples of spanning. So we will see the theorem on this linear span in the next lecture.